In this video, we will learn oxidation and reduction reactions of carboxylic acid derivatives, such as esters, anhydrides, acid chlorides, and amides, not to mention the parent carboxylic acid. We will continue to use the carbonyl grid to organize both what we will learn today and integrate it into our existing knowledge of these functionalities and other carbonyl-containing functional groups such as aldehydes and ketones and their derivatives, alcohols, acetals, etc. Learning goals for today are to be able to predict the products of redox reactions to carboxylic acid derivatives, provide complete curved error mechanisms for these reactions, evaluate the relative reactivity of carboxylic acid derivatives and common reducing agents. Well, clearly we'll be using that ladder of reactivity, right, where acid chlorides are the most reactive and carboxylates are the least reactive acid derivative. Thinking about common reducing agents, for aldehydes and ketones, these were hydride donors and carbanions. The hydride donors we encountered were sodium borohydride and lithium aluminum hydride. The carbanions that we encountered were Grignard reagents and organolithium reagents. Organocuprates did not react with aldehydes and ketones. These are reduction reactions quickly because adding hydride followed by protonation will generate an alcohol. We can see that the number of bonds between the carbonyl carbon and oxygen were reduced. That's an example of adding hydride to an aldehyde. Adding a carbanion to a ketone, followed by acidic workup, also represents a reduction reaction, where again, 2 bonds to oxygen has been reduced to 1 bond to oxygen. Perhaps these reducing reagents will show up again today. And finally, we will propose synthetic pathways involving oxidation and reduction reactions of carbonyl compounds as key steps. Let's get started. As we go along today, we will be adding these reactions to our reaction chart, and you should be keeping one at home yourself as well. By now, the carbonyl grid should be a familiar sight. Keep in mind it is simply a synthetic tool that helps you consider the transformations between different carbonyl-containing functional groups. There are some reactions we've learned that are not on this grid, such as those of anhydrides and those to, say, tertiary alcohols. Be sure that you review the acyl transfer quadrant down in the lower right-hand part of the grid. No redox occurs in that section of the grid. Review the reactions you already know, labeled in green. In particular, these 3 reactions, which represent reductions, will be particularly relevant today. That is, of course, because this video is about oxidation and reduction reactions to acid derivatives. We will begin with reduction. These are the 3 boxes you already know for aldehydes and ketones being reduced to make primary and secondary alcohols. Be sure you review these boxes. And now we're going to zoom in on this lower left-hand quadrant that represents the reduction reactions of acids, acid chlorides, esters, and amides. And here we are on that zoom in of that lower left quadrant. We will begin now with the highlighted column. This column represents the synthesis of primary alcohols. If you'd like, you can draw in the implied hydrogen that is missing from that carbon since one was already there. And then I've highlighted in pink the carbon that either is or was the carbonyl carbon. Let's start by describing what bonds will be made and broken for each of these 4 transformations. For this square, it's acid to primary alcohol. For the next square, it'll be acid chloride to primary alcohol. The final 2 squares represent ester to primary alcohol and amide to primary alcohol. Once you have the generic transformations written out, try yourself to think about what bonds are made and broken. Well, in each case, the bond between the carbonyl carbon and X, what we called generically X when we were discussing acyl transfer reactions, those bonds are broken. And in fact, these groups we expect will be leaving groups because a sigma bond is being broken and those X groups are completely leaving the molecule. There's no longer a bond between the carbonyl carbon and OH or Cl or 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 the amino group. We can see in each case the carbonyl bond, the pi-CO bond is broken, but the sigma bond is retained. You can see the bonds are made in the product between two hydrides and the carbonyl carbon. And then a little bit more boring, there's the OH bond that's made, and that will happen in a proton transfer step. So for each of these transformations represented here, two equivalents of hydride are adding to the carbonyl carbon. Let's write that down. And then the X group leaves. That does represent a net reduction, where, for example, in the carboxylic acid, there are 1, 2, 3 bonds between the carbonyl carbon and more electronegative atoms, in this case, oxygen. In the primary alcohol, there's only one bond between what was the carbonyl carbon and a more electronegative atom, oxygen. Thus, 3 bonds to 1 bond represents a reduction. We may make a prediction here. What reagents do you expect will be used to donate hydride to the carbonyl carbon? Sure, we might expect to see sodium borohydride or lithium aluminum hydride, as they were used for similar transformations to aldehydes and ketones. Right when I asked you to fill in these two boxes, this is what you had there. Excellent. So the reduction quadrant will have strategies, just like we had strategies for the acyl transfer quadrant. And our first strategy for column number 1 is that anything but an amide can be reduced directly to form a primary alcohol. So there's going to be some direct way to convert these 3 functional groups, carboxylic acid, acid chloride, and ester, into primary alcohols. But the amide will not be direct, so let's just write not direct. Okay, and let's get started. Let's learn what these reactions are that directly convert these 3 functional groups into primary alcohols. We will start with the ester. When esters are treated with lithium aluminum hydride, followed by an aqueous acidic workup, such as dilute hydrochloric acid, primary alcohols are observed. Looking at the overall transformation, it appears that 2 equivalents of hydride have been added to the ester, and specifically to the carbonyl carbon of the ester. Given how polar pi bonds react, I would ask you to take a moment and propose a complete curved error mechanism for this transformation before listening to me explain it. Understanding that polar pi bonds undergo addition-elimination reactions with nucleophilic species such as hydride and others, such as diagrammed at the top of the page. We may propose a similar mechanism for the reduction of esters with lithium aluminum hydride, and this clearly is a reduction. The carbonyl carbon has 3 bonds to oxygen in the ester and 1 bond to oxygen in the primary alcohol. We can show the sigma electrons between aluminum and hydrogen, or we can simplify and just pretend there's a hydride. Choose one method. It doesn't matter which you use. Choose one though. Showing that nucleophile adding to the polar pi bond in a nucleophile addition elementary step generates a tetrahedral intermediate that looks like this, where this new bond has been formed between hydride from lithium aluminum hydride and the carbonyl carbon of the ester. LAH certainly qualifies as basic conditions, and we can see that so far the curved arrow mechanism is following the general pattern for acyl transfer reactions under basic conditions, which is a nucleophile addition followed by a nucleophile elimination from the tetrahedral intermediate. Looking at the ester, we can see it does indeed have a leaving group. Although not a great leaving group, under basic conditions, alkoxide is a leaving group. And nucleophile elimination, lone pair push, collapse of the tetrahedral intermediate, nucleophile elimination does indeed generate, once again, that carbonyl CO double bond, which is quite strong. And this is certainly entropically favored as well, as it releases a molecule of alkoxide. Now you may notice this intermediate that is formed is an aldehyde, and we already know what aldehydes do in the presence of lithium aluminum hydride. They react. They are even more reactive than esters. In fact, aldehydes are more reactive than esters to nucleophiles. There is a bigger partial positive on the aldehyde carbonyl carbon than the ester carbonyl carbon. And so the aldehyde reacts with another equivalent of lithium aluminum hydride. Again, you can either show the sigma electrons of the aluminum hydrogen bond or just write an H minus. Either way, another nucleophile addition step takes place. You might not want it to, and you might want to stop at the aldehyde. You do not have a choice, however, because aldehydes react with lithium aluminum hydride. So this cannot be stopped. This nucleophile addition step does generate another tetrahedral intermediate. This time, however, there are no leaving groups. There's hydride and there's carbanion. Those are not going to be good leaving groups because they are not stable conjugate bases. So in fact, this is not a reversible nucleophile addition. It is irreversible because there are no leaving groups. So let's write that down. This is irreversible. Hence the title of the slide. So when this alkoxide intermediate is generated, that's it until the acidic workup. When treated with an aqueous acid, the alkoxide is protonated in a proton transfer step to generate the neutral product, the primary alcohol, as shown by these curved arrows. Wonderful. So esters react with lithium aluminum hydride to generate primary alcohols. Now we know what to put for the ester. Write down any questions that you have at this point. Well, I have a question for you. How do you think that acid anhydrides and acid chlorides will react under the same conditions with lithium aluminum hydride? Do you think they'll make primary alcohols under those conditions? Well, yes. So esters, anhydrides, and acid chlorides will all react with lithium aluminum hydride followed by an aqueous acidic workup to generate primary alcohols. It may help to label the carbonyl carbons. And the anhydride is maybe a bit tricky. It's a cyclic anhydride, and there are 2 carbonyl carbons, and we maybe don't quite know what's going to happen. It also is useful to remember that the alkoxy group, at least for the ester, that will leave. We do expect that at least one of these carbon-oxygen bonds will be broken for the anhydride. And we expect the same for the acid chloride. So pause and please predict the products of each of these reactions based on what you now know. Following the pattern that we just discussed, the ester will be reduced with 2 equivalents of hydride, breaking the carbonyl oxygen pi bond, leaving the sigma bond intact, and the alkoxy group will leave, yielding a primary alcohol, which you could draw like this, or you could draw without the implied hydrogens. That is certainly up to you. I'm showing the implied hydrogens just so we can think about what exactly happened here, what bonds were made and broken. Now for the anhydride, I just left you to your own devices, but I will let you know that both of these carbonyls are reduced. So we will add 2 equivalents of hydride to each of these carbonyls. After workup, generating a diol that looks like this. Whoa, how did she get that? Number your carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, and then this oxygen is just gone. It has left. Just like the alkoxy left, it became an alcohol. This oxygen left and becomes water. And if you're screaming, how, at the computer, I'll show you how in a minute. Just play along for now. All right, for the acid chloride, it also behaves like an ester, and this chloride's going to leave. The carbonyl double bond is going to break, but the single bond remains intact. And guess what? You'll get the same exact product as we did for the first problem. You can see the acyl group for the ester and the acid chloride. Those 2 acyl groups are exactly the same. So when treated with lithium aluminum hydride, the same primary alcohol is obtained. Take a moment before you move on and add these reactions to your reaction chart. We learned 3 reactions. So the reductions of acid chlorides or anhydrides with lithium aluminum hydride, followed by an aqueous workup. And then we learned the reductions of esters with lithium aluminum hydride. So be sure that you fill these in. Once you have completed your reaction chart entries for those 3 reactions, let us move on. I'll go right back here to the grid. You can now fill in this square. It is indeed the same as for the ester. And that's what we predicted based on the rule down there. The rule says anything but an amide can be reduced to directly form our primary alcohol. What about the carboxylic acid? Do you think it's going to behave the same way? Let's find out. Can carboxylic acids be reduced with lithium aluminum hydride? Pause, make a prediction, write down your reasoning. Well, I wish I could hear everyone's predictions, but I can't. So let's go ahead and move on. You can listen to my answer at least. Lithium aluminum hydride constitutes basic conditions. It is a basic source of hydride. Sodium borohydride is a more nucleophilic source of hydride. It's compatible with alcohols and water. Lithium aluminum hydride is not. It is basic and it is incompatible with alcohols and water. Alcohols and water have pKa's around 16. So when a carboxylic acid is treated with lithium aluminum hydride, what do you expect is the first thing that happens? Yes, a rapid proton transfer reaction. Rapid. And I've written this as an equilibrium, but it is essentially irreversible. Think about the conjugate acid of lithium aluminum hydride. It's hydrogen gas. Goodbye. It bubbles away. Not only is it not acidic, it's a gas. So it leaves. It really is unavailable to react in the reverse direction. So essentially, this is irreversible. So I'm going to erase that backwards arrow. And what has been formed? Carboxylate. And what do we know about carboxylate? They are the least reactive carboxylic acid derivative. They are electron rich. So they are not very reactive with nucleophiles, which are also electron rich. Likes repel, opposites attract. Given this information, would you like to change your prediction? Well, I don't know what you predicted, so I can't tell you if it's a good idea or a bad idea to change your prediction. But you already know the answer to this question. This question of, well, will the carboxylate now react with LAH? You already know. Think about the anhydride on the previous page, right? We saw the anhydride reacted. Both carbonyls of the anhydride reacted with 2 equivalents each of LAH to form the diol. If we think about how that happens, abbreviating LAH as just simply hydride, there is the first irreversible nucleophilic addition step, generating this tetrahedral intermediate, which has a good leaving group. The carboxylate is a good leaving group. So we'll show collapse of the tetrahedral intermediate, nucleophile elimination to generate this intermediate, where there's an aldehyde and a carboxylate. Oh, just a brief aside. So some of you wondered, well, why is she calling this whole thing a leaving group? Well, I'm calling this whole thing a leaving group because the lone pairs on this oxygen that come from the electrons in this bond here, they're not isolated, right? They're conjugated to the carbonyl, and that makes these electrons more stable than they would be, say, on just an alkoxide. Like they're much more stable than, say, the negative charge on an alkoxide. So that's why I circled the entire group, because the lone pairs on the oxygen are conjugated to the carbonyl. All right, so there's an aldehyde that we know is further reduced. It's even more reactive than esters. And this carboxylate, well, we didn't previously know that it would react with LAH, except for that I told you on the previous slide that this goes all the way to the diol, meaning that both of these carbonyl carbons react with 2 equivalents of hydride to generate this final product. If that is indeed the case, then that lets us know that carboxylates do react with lithium aluminum hydride. There's no other way these 2 hydrogens get on that carbonyl carbon except by carboxylate reacting with lithium aluminum hydride. That is how reactive lithium aluminum hydride is. It is so reactive, it even reacts with carboxylates. Wow. So in fact, another equivalent of lithium aluminum hydride, this time I've drawn out the aluminum hydrogen bond, but again, if you just wanted to put H minus, that would be okay. It does react with the carbonyl in an irreversible addition. The tetrahedral intermediate that is formed is not gonna expel hydride because it is not a good leaving group. It's super basic, as we're coming to realize. So addition of hydride generates this tetrahedral intermediate. It's dianionic, and it is in fact converted to the primary alcohol. Well, how does that happen, you might ask? This looks crazy. It's a dianionic intermediate. There are no leaving groups. I mean, obviously, O2 minus is not a leaving group. No, yikes. My chemical intuition does not like that. Well, there is aluminum around, and aluminum certainly will coordinate to oxygen. And we're really not going to worry about exactly how this happens. I'm just going to give you enough that you can get the basics. Okay, so aluminum in some form has bonded to oxygen. Lithium is still floating around here. And so this oxygen bonded to aluminum, that actually is a decent leaving group. So that's all going to leave together. That will generate an aldehyde. And we already know, as we have said, aldehydes are reactive with LAH. So this will continue to be reduced by hydride. And then there will be the workup step to add that proton. So there'll be one more nucleophilic addition with hydride, followed by proton transfer. Now, of course, if I asked you to show this mechanism on an exam, you would need to draw these out, but I probably wouldn't ask this one just because this part where oxygen is coordinating to aluminum is kind of tricky. Wonderful. We've got it. Now we can add yet another reaction, both to the grid and to our reaction chart. So indeed, these same conditions convert acids to primary alcohols. It's because two equivalents of hydride are added, and it happens via an aldehyde intermediate. We've added that to the carbonyl grid. Now we'll add it to our reaction chart. Here we are, reductions of carboxylic acids with LAH. Fourth reaction we've learned today. Just moving right along, right? Just as the case for the other three reactions, primary alcohol is the product. Same primary alcohol, because for each of these generic molecules, I've chosen the same acyl group. So there we go. And two equivalents of hydride. You can choose whatever generic molecule you would like, though. This is fun, right? Not so bad. We already know about lithium aluminum hydride. We already know the general mechanisms for nucleophile addition under basic conditions. We're just rolling right along. Take a look at this slide here and explain why each of these reactions, 1, 2, 3, 4, gives benzyl alcohol as the only organic product. Propose a complete curved error mechanism for each of these reactions. As I have already shown you how each of these functional groups reacts with lithium aluminum hydride, please compare your answers to the mechanisms that I've already shown you. Of course, the molecules are slightly different, so they'll look a bit different, but the elementary steps are the same. Then once you're convinced, time to move on. And we will move on to this question. What other functional groups can be reduced with LAH? So recall your prior knowledge. I'll give you some hints. Ketones can be reduced with LAH, as can aldehydes, nitriles, and amines. You have learned all four of these transformations before. So if you have not already filled in this table, please do so now. It's like a little mini reaction chart. Last chance. Ketones are reduced to secondary alcohols, where hydride adds at the carbonyl carbon, followed by protonation at oxygen. Nitriles react to form amines, Again, where LAH adds 2 equivalents at the carbon of the nitrile this time. In fact, there are 2 pi bonds here, so 2 equivalents of hydride can add, followed by protonation of nitrogen. We have discussed this mechanism before, and I encourage you to review it if you would like. Aldehydes are converted to primary alcohols. Just comparing to ketones, there's 1 hydrogen already on the aldehyde, so that remains. That's really the difference. The ketone has 2 alkyl groups to begin, and it has 2 alkyl groups to end. The aldehyde has 1 alkyl group to begin and 1 to end. Thus, aldehydes are converted to primary alcohols. Hydride adds to the carbonyl carbon, and then the aqueous workup protonates oxygen. Finally, amines are converted to secondary amines in the presence of lithium aluminum hydride, followed by an acidic workup. Lithium aluminum hydride adds hydride to the amine carbon, the carbonyl-like carbon, and the aqueous workup protonates nitrogen. Wonderful. And we'll add one more here that I'll just show you right now. Amides are converted to amines under these conditions. Ultimately, 2 equivalents of hydride from LAH do add to the carbonyl carbon. Oxygen actually leaves in that process, just like we saw for the carboxylate. And so after oxygen leaves, we have this iminium, which of course is reduced again with hydride to generate the final amine. Awesome, well let's add this last transformation to our carbonyl grid. Yeah, amides were the only functional group that cannot be directly converted to a primary alcohol with lithium aluminum hydride. So it's certainly worth noting that treatment with lithium aluminum hydride generates the primary amine. Amide still reacts with, as we said, 2 equivalents of hydride. So to convert the amide to a primary alcohol, this would have to go via any of these other functional groups. You can review the acyl transfer grid to figure out the best way to do that. Moving right along, reductions of amides with lithium aluminum hydride generate amines. And whether or not it's primary, secondary, tertiary amine, it just really depends on what the R groups are. Okay, a few more reactions to go here. It's more than it looks, I hate to say that. And you can probably tell from the slide count. All right, we've reviewed how functional groups react with LAH. We learned some new reactions as well. Let's think about other reagents that are hydride donors and what functional groups they react with. I can give you some hints. There's 2 hydride donors we've previously discussed, sodium borohydride and sodium cyanoborohydride. So see if you can remember the reactions involving these 2 species. Although sodium borohydride is less reactive than LAH, it still reduces ketones and aldehydes to secondary and primary alcohols, donating hydride to the carbonyl carbon, and it does so in the presence of an alcohol solvent or even water. And that's partially how we know that sodium borohydride is less reactive than lithium aluminum hydride. Sodium borohydride is compatible with mildly acidic protons, whereas lithium aluminum hydride certainly is not. Bottom line, even though sodium borohydride is less reactive than lithium aluminum hydride, both reagents reduce aldehydes and ketones to the same primary and secondary alcohol products. And that just simply means that aldehydes and ketones are electrophilic enough to react even with the weaker nucleophilic agent, sodium borohydride. In contrast, sodium cyanoborohydride is even less reactive than sodium borohydride, and it does not reduce aldehydes and ketones. In fact, a ketone, such as this one, can be treated with an amine in the presence of sodium cyanoborohydride in a slightly acidic buffer, and that ketone will not react with the reducing agent. However, the ketone does react with the nucleophilic primary amine or secondary amine. The primary amine is just an example, so let's write that down, or a secondary amine, to generate an iminium ion. That iminium ion has a positive formal charge on nitrogen, and it is even more reactive than the ketone. And sodium cyanoborohydride does react with the aminium ion. Although it is weakly nucleophilic, it's nucleophilic enough to react with that species to generate this amine product. And so answering the question, what are other hydride donors that we know and what functional groups do they react with? We know that sodium borohydride reacts with aldehydes and ketones, although it is less reactive than lithium aluminum hydride. And sodium cyanoborohydride only reacts with aminium ions. Once you've got it, well, let's keep going. We'll predict the products of these two reactions. Ready, set, go. Our first step is identifying the functional group and the reactant. There's a ketone and an ester. Both of these functional groups react with lithium aluminum hydride. The ketone will react with one equivalent of hydride and generate, after the workup step, a secondary alcohol. The ester will also react with lithium aluminum hydride, as we know. However, it's a tad more complicated. We know that the bond between the alkoxy group and the carbonyl carbon will be broken, and the alkoxy group will leave. So ultimately, after workup, that alkoxy group will be converted to an alcohol. Two equivalents of hydride will add to the carbonyl oxygen. Because once the alkoxy leaves, you'll have an aldehyde, so two equivalents will add. Whereas both functional groups were reduced with the reactive lithium aluminum hydride, generating the secondary alcohol from the ketone and the primary alcohol from the ester. When this same compound is treated with sodium borohydride, only the more reactive ketone will be reduced, resulting in a product that retains the ester but includes the reduced secondary alcohol from the ketone. And this really is the point of this slide. Esters are unreactive with sodium borohydride. Make sure you have that down because I do want to just pose one more question to you. Could we imagine taking this same reactant, so this reactant that has the ketone and it has the ester, and somehow converting it to the primary alcohol where the ketone is maintained? What do you think? How will we do that? Yeah, well, we know the ketone is more reactive. The ketone reacts with lithium aluminum hydride and sodium borohydride. We know that the ester only reacts with lithium aluminum hydride as far as in a reduction reaction. So if hydride is added, it certainly is from reaction with LAH. So in that case, you better protect that ketone. We'll protect the ketone as what? Yes, as an acetal. I'll just use a cyclic acetal with a diol and catalytic acid. Then we'll reduce the ester. Now that the ketone is protected, it will not react, right? Acetals are stable under basic conditions. And then finally, we will treat with the aqueous workup, and we'll just say, hey, you know what? Aqueous acid also deprotects acetals. So it'll be the workup, and it will deprotect the acetal to reveal again the carbonyl. All right. Let's just add a few things to the grid and to our reaction chart. So what we're going to add to the grid is this. Acids and anhydrides, they can be reduced with LAH or sodium borohydride. Acids, it is only lithium aluminum hydride that reduces. Remember, acids is the bottom of the chain, right? Made the carboxylate, it's really unreactive. So only the strongly reactive LAH will reduce it. Esters, only LAH will reduce it, no sodium borohydride. And same with the amide, only LAH will reduce it to the primary amine. Right, now that we've added those notes to the grid, and we're going to discuss this relative reactivity more in a minute, so if you're not really sure what I'm talking about quite yet, you'll have another chance to think about it and add those notes to the grid. And you will notice something here. So it says reductions of acid chlorides or anhydrides with sodium borohydride or LAH. Reductions of esters with LAH, so only LAH. Esters are unreactive with sodium borohydride. You'll see reductions of carboxylic acid with LAH. They are also unreactive with sodium borohydride. Same thing for the nitriles or amides. We only have LAH listed. But for acid chlorides and anhydrides, could also use sodium borohydride in the presence of proton source. All right, moving along. Let's summarize this whole discussion of relative reactivity. Quickly add to this list any missing functional groups containing polar pi bonds. Then identify which functional groups will be reduced with each of the 3 reducing agents discussed so far. Finally, explain any trends. Please, it's important, pause and try on your own. Aldehydes and ketones are missing, and we know that they are more reactive than esters. We also know that aminium ions are a bit more reactive than aldehydes and ketones, so they go above it on the reactivity ladder. Of the reducing agents, lithium aluminum hydride is the most reactive. Sodium borohydride is the next most reactive, with the weakest reducing agent being sodium cyanoborohydride. Lithium aluminum hydride reduces all of these functional groups, every single one. It is the most reactive. Sodium borohydride reduces just those at the top, acid chlorides, anhydrides, aldehydes, and ketones. Finally, thinking about sodium cyanoborohydride. It's the least reactive reducing agent. We've really only seen it used with aminium ions. I am sure it will also reduce acid chlorides and anhydrides, but it's used specifically for aminium ions because the aminium ion can be generated and then selectively reduced in the presence of an aldehyde or a ketone. Good. So if it was unclear before, hopefully it's more clear now. You can add those notes to your grid and your reaction chart. One more point before I move on is that there's one more reagent that we have encountered that includes hydride, and that is just simply sodium hydride. For those of you who are wondering where sodium hydride falls in here, it doesn't. So sodium hydride is a basic source of hydride. It really reacts as a base, but not so much as a nucleophile. And it won't reduce any of these species. It might deprotonate them, but it will not reduce them. So we know that esters do not react with sodium borohydride. They're just not electrophilic enough, and sodium borohydride is a weaker reducing agent than LAH. Esters do react with LAH, but 2 equivalents of hydride are added to generate primary alcohols. Keeping that in mind, please provide reagents for the following desired transformation. Now, we don't know how to go directly from an ester to an aldehyde. We know that this is certainly a reduction reaction, where the carbonyl carbon in the ester has 3 bonds between carbon and oxygen, 1, 2, 3, while the aldehyde carbonyl carbon has 2 bonds between carbon and oxygen. So certainly this is a reduction reaction. And the only reducing reagent that we currently know that reacts with esters is lithium aluminum hydride. However, lithium aluminum hydride, after aqueous acidic workup, does generate the primary alcohol, not the aldehyde. So how to convert the primary alcohol into the aldehyde? Well, you already know how to do that. This is an oxidation, right? Primary alcohol, 1 bond between carbon and oxygen. Aldehyde, 2. So this is an oxidation reaction. And to stop at the aldehyde rather than the carboxylic acid requires a dry anhydrous chromium reagent. So PCC, pyridinium chlorochromate, in the presence of an organic solvent. Okay, so it's a bit clunky here. We're reducing all the way to the primary alcohol and then oxidizing back up to the aldehyde. but currently this is the only way that we know to affect this transformation. I'm about to show you something beautiful, but we're not there yet. So something beautiful will be happening in a minute. But for the meantime, we have this clunky reduction oxidation transformation from ester to aldehyde. And that's because in the ester reduction, as we discussed, now the aldehyde is the intermediate, and they're super reactive with LEH. We're going to move on now to this third column of the reduction quadrant of the grid. This third column represents making aldehydes. Just as before, all the X groups are leaving. Hydroxide, chloride, alkoxide, amide, they're all leaving in this transformation. But unlike the primary alcohol column, in which 2 equivalents of hydride were added, to generate the aldehyde, we only need just one equivalent of hydride. Let me just show that esters can be reduced to form aldehydes. That's the guiding principle for column 3 here. The ester can be directly converted, but then everything else, I think we just expect these reduction reactions will be via the ester. Currently, we have this clunky scheme, reduce and oxidize. Why can't we just go directly to the aldehyde? Why can't we do it? Well, we already know why we can't do it. Here's the mechanism for the reduction of esters with lithium aluminum hydride that we have previously discussed. The carbonyl carbon undergoes irreversible nucleophile addition with hydride from lithium aluminum hydride. This tetrahedral intermediate does undergo nucleophile elimination of the alkoxy group, which is a leaving group, and that generates this aldehyde. And this aldehyde intermediate is even more electrophilic than the ester and continues to react with lithium aluminum hydride in a second irreversible nucleophile addition step, making both of these bonds between what was the carbonyl carbon and hydride. So they're implied in the product, but for a moment I'll draw them here for you. Finally, after workup, the alkoxide is protonated, forming the neutral alcohol. All right, so what is the problem here? Why can't we just stop the reaction at the aldehyde? Well, the problem is aldehydes are more reactive than esters in nucleophile addition steps. Okay, so that's the problem, right? Let's keep that in mind as we consider this question. Is there any way to just add one equivalent of hydride to the ester? Well, I would say maybe, but we have to avoid formation of the aldehyde because that is going to keep reacting. So what we currently know how to do is to add 2 equivalents of hydride to an ester. One more time. That is via the aldehyde with lithium aluminum hydride. That's fine. But remember when we went and we reoxidized this back up to the aldehyde? That's just ugly, right? Chemists want to be able to accomplish this transformation to the aldehyde without this ugliness. This is inelegant. A reduction, then oxidation, you waste chromium, you got to use methylene chloride. This is just, no, we don't like that. The chemist would like to take the ester and directly, elegantly reduce it to the aldehyde. So how can we add one equivalent of hydride to an ester? The strategy is to form a stable tetrahedral intermediate. If the tetrahedral intermediate resulting from nucleophile addition of hydride to the ester does not collapse, if this can be avoided, the nucleophilic elimination can be avoided, then no aldehyde will be formed and no further reduction will occur. Now, there is a reagent that allows this transformation to occur. So when an ester is carefully treated with a diisobutyl aluminum hydride, which goes by several acronyms, dibal-H, diba, and dibal, at low temperatures, an aldehyde is recovered following an aqueous acidic workup. Let's explain this observation with a complete curved arrow mechanism. The aluminum atom in diisobutyl aluminum hydride has an empty p orbital to which the oxygen can coordinate. At the same time this coordination is happening, the electrons in the aluminum hydrogen bond add to pi star CO in a nucleophile addition step. This nucleophile addition results in a tetrahedral intermediate that looks like this. Because of the coordination between aluminum and oxygen, this tetrahedral intermediate is stable at -78 degrees Celsius. So because oxygen is using its lone pair to make a bond to aluminum, there is no lone pair push, no expulsion of the alkoxy, no formation of the aldehyde. So upon acidic aqueous workup, step 2, the aluminum-oxygen bond is hydrolyzed, and we won't show the mechanism for that. And any remaining reductant reacts with water, resulting in this hemiacetal. Under acidic aqueous conditions, the hemiacetal is protonated to make the alkoxy group a good leaving group. Now, obviously, either oxygen can be protonated, and they both certainly are, but protonation of the alkoxy group is productive down the reaction pathway for which we are drawing the curved arrow mechanism. So that is the proton transfer reaction we will worry about right now. That proton transfer reaction generates a good leaving group. This tetrahedral intermediate now can collapse, lone pair push, nucleophile elimination, expel the good alcohol leaving group to generate the protonated aldehyde, as well as a molecule of alcohol. One more proton transfer step yields the final aldehyde product, as shown. Eureka, we've done it. Direct conversion of esters to aldehydes, all by avoiding formation of the aldehyde intermediate by making a stable tetrahedral intermediate. Add this reaction to our reaction chart. Esters, such as this one, when treated with dibal, which is sometimes, like I said, called dibal H, and I kind of like that because it shows the hydride, followed by acidic aqueous workup, generates the aldehyde, and of course an equivalent of whatever alcohol was bonded to the ester, but usually that's just considered a byproduct and separated. All right, it's on our reaction chart, and we can add it to this slide as well. Now we know a much better way to convert esters to aldehydes just directly with dibal H at low temperature followed by acidic aqueous workup. Of course, you can also add that right here, and I'll have you do that. You have the inelegant or the elegant method for converting esters to aldehydes, or put them both in there. You're fully equipped to fill in the first and third columns of the carbonyl grid. Now let's focus about the second and fourth columns. Think about what bonds will be made and broken for each of the transformations represented by these columns. Just as for generating primary alcohols and aldehydes from acid derivatives, we expect that the X groups will leave when we generate secondary alcohols and ketones, right? There's no more hydroxyl in the ketone. Well, there is one in the secondary alcohol, but we're pretty sure that oxygen is from the carbonyl oxygen. So the X groups leave. Now, unlike primary alcohols and aldehydes, for columns 2 and 4, we're adding R groups. Now for column 2, we expect to add a carbanion, and it looks like, let's zoom in a bit, so a carbanion and a hydride. For the ketone, looks like just a bond to a carbanion is made, so a carbon-carbon bond is made. We think these reactions will proceed by a nucleophilic addition, nucleophilic elimination, elementary steps. That makes sense. All these reactions to polar pi bonds have been occurring that way. Now, what might be the source of carbanion? Grignard reagents, organolithium reagents, dialkyl cuprates. And we've also talked about Wittig reagents, but those generate alkenes. An interesting aspect of these two columns is that they could be interconverted between each other, right? So the ketone, if you could say take the carboxylic acid into the ketone can be converted to a secondary alcohol, right? Ketones to secondary alcohols, we know those transformations already. Ketone to secondary alcohol, right there, we know that transformation. Now you can use sodium borohydride or lithium aluminum hydride in the presence of an alcohol solvent. Secondary alcohol to ketone, well, we know that as well. We can use any of the oxidation conditions we've learned, such as PCC, pyridinium chlorochromate, in the presence of methylene chloride solvent. Oh, well, that's interesting. Yes, because we just looked at how esters react with lithium aluminum hydride. So make that analogy here. So predict the major organic product of the reaction of this ester with ethyl Grignard. Then provide a complete curved error mechanism for the formation of this product. I predict that the very reactive Grignard reagent will add 2 times to the ester like LAH does. And since these are basic conditions, it will occur directly to the neutral ester. So either showing the sigma electrons in the magnesium-bromine carbon bond, or drawing up the Grignard reagent as a carbanion and having those electrons attack. Either way is fine. And this nucleophile addition step results in the following intermediate. This tetrahedral intermediate contains a leaving group, the ethoxy group that we anticipate will be leaving and no longer in the product. Collapse of the tetrahedral intermediate, lone pair push, nucleophile elimination, generates this ketone. Now, although this nucleophile elimination step is reversible, the ethoxide could just add back, generating a tetrahedral intermediate again. The initial nucleophile addition step is irreversible, meaning that lone pair push would not expel out the carbanion to generate the starting materials again. So it's irreversible. Carbanion is not a leaving group. Now, from this ketone intermediate, the reaction continues because, as you know, ketones are more reactive than esters. A second equivalent of the Grignard reagent adds to this ketone irreversibly to generate this alkoxide. We can see indeed 2 equivalents of the carbanion have added. This alkoxide is a stable intermediate and does not react anymore until the acidic aqueous workup. Protonation of the alkoxide with aqueous acid generates a final tertiary alcohol product, where indeed, as we predicted one more time, 2 equivalents of the Grignard reagent have added. So sometimes you'll see excess listed by the Grignard reagent for these transformations. We'll add this reaction to the reaction chart we have been building together. So it says reductions of esters, etc. So let's put the ester. Treatment of an ester with excess Grignard reagent followed by an acidic aqueous workup generates a tertiary alcohol and whatever the alkoxy group was from the initial ester, which often is treated as a byproduct and separated from the desired organic product. This transformation works when esters are treated with Grignard reagents or organolithium reagents. A similar transformation also occurs to acid chlorides and anhydrides with either Grignards or organolithiums. If either an anhydride or an acid chloride is treated with a Grignard reagent followed by aqueous acidic workup, or instead of a Grignard, an organolithium reagent, tertiary alcohols will be observed. For the anhydride, the acetate leaving group will be formed instead of the alcohol, and for the acid chloride, the chloride leaving group will be formed instead of the alcohol. The mechanism for those reactions is identical to what we just learned for the reactions of esters with Grignard reagents. It's just that the leaving group will be different. You can work out those mechanisms and let me know if you have any questions. Where does this reaction go on our grid? Nowhere. So we said we're going to start with esters plus Grignard reagents, and it leads us off the grid, right? Esters plus Grignards leads us to tertiary alcohols, which are not one of the products on the carbonyl grid. Esters plus Grignards make tertiary alcohols. Even though they're off the grid, we need to be familiar with that reaction. Okay, and as we discussed, acid chlorides and anhydrides will undergo the same reaction, also to generate a tertiary alcohol. Quick note, carboxylic acids would just be deprotonated by Grignards and organolithium reagents. Yikes, there's that acidic proton there, so they're incompatible. Well, that was fun, but it didn't take us to make either the secondary alcohol or the ketone. And that's really because these 2 equivalents of R were added. We want to add 1 equivalent of carbanion, not 2. So it's a really similar problem to what we had with reducing esters directly to aldehydes. In LAH reduction, we saw an aldehyde intermediate, which immediately continued reacting with the hydride donor to form the primary alcohol. With methyl magnesium bromide, we saw a ketone intermediate, which is also more reactive than an ester and continues reacting with methyl magnesium bromide, forming the tertiary alcohol. So ultimately, 2 equivalents of carbanion were added to the carbonyl carbon of the ester. Now for hydride donors, we found a solution. We used dibal, which avoided formation of the aldehyde, and it was only formed on the workup. So then we were able to isolate the aldehyde product, only add 1 equivalent of hydride to the ester. Will there be a solution for carbanions? Will there be any way to add 1 equivalent of carbanion to carbonyl carbon of an ester? I don't know. Let's provide reagents for the following transformation. And you can see in this transformation, 1 equivalent has been added. So can we figure out some way to do this? Right now, just using reactions we already know. So think about it for a minute. Well, although 2 equivalents of carbanion add to esters, only 1 equivalent of a carbanion can add to an aldehyde because it does not have a leaving group. So what if we converted the ester to an aldehyde? Then treat the aldehyde with the desired Grignard. It's a 2-carbon carbanion there. 2-carbon Grignard is required, followed by acidic aqueous workup. This generates a secondary alcohol, and we already know how to convert secondary alcohols into ketones, any of the oxidation conditions that we have learned. We've discussed this a couple times today. That final oxidation just reverses this initial reduction, so this is a bit inelegant, but we have added only 1 equivalent of carbanion because we did so to the aldehyde, which doesn't have a leaving group. H is not a leaving group like alkoxy is. So 1 equivalent can be added. We can summarize this discussion about strong nucleophile donors reacting with esters twice on this slide. So here we have LAH reduction of an ester. We have Grignard reduction of an ester. In both cases, 2 equivalents of the nucleophile adds to the ester carbonyl carbon. We talked about how to add 1 equivalent of hydride to esters first with this inelegant redox strategy, reduce all the way, and then oxidize back up to the aldehyde. And then we learned the beautiful direct route, right? We used a less reactive reductant, essentially dibal. We were able to add just 1 equivalent of hydride. We just discussed the inelegant strategy for adding 1 equivalent of carbanion to an ester. That involved dibal reduction to make the aldehyde. The aldehyde is then treated with methyl magnesium bromide, yielding a secondary alcohol, which we would oxidize back up to the ketone. Wow, that's a lot. Is there some easier way to go directly from an ester or something like an ester to a ketone? Is there some magical equivalent of dibal that we can use to add 1 equivalent of carbanion, like we were able to add 1 equivalent of hydride? Let's briefly review the different types of carbanion delivering reagents, aka organometallic reagents. We've previously discussed that organolithium reagents undergo direct addition to the carbonyl of alpha-beta unsaturated ketones, whereas Grignard reagents undergo a mixture of direct addition and the conjugate addition product, addition to the beta carbon, and cuprates undergo conjugate addition as the major pathway of reactivity with alpha-beta unsaturated ketones. And this is because organolithiums are the most reactive of these 3 carbanion-like species. Grignard reagents are the next most reactive, and the dialkyl cuprates are the least reactive of these species. Can the relative reactivity of these different sources of carbanions help us solve the problem at hand? Well, let's talk about that. So we know that organolithiums are the most reactive, then Grignards, so organomagnesium species, and then cuprates. Grignard reagents react with, so far we've discussed these 4 species. I'll tell you they will also act with amides and they will also act with nitriles. We've discussed that before in the previous unit. Grignards do not really react with carboxylates though. Now, organolithiums, which are the most reactive of our carbanion delivering species, they actually react with, as you would expect, all 6 of these functional groups and carboxylates. Whoa, organolithiums are so reactive, they even react with the electron-rich carboxylate. What about cuprates? Which of these polar pi bond containing functional groups do you think that cuprates may react with? Well, as it turns out, they react with acid chlorides. And what's really significant is they do not react with aldehydes and ketones. Why is that significant? That is significant because remember the problem with Grignards. Ketones were an intermediate and they react with Grignards, but ketones do not react with cuprates. Unfortunately, cuprates do not react with esters, so we can't use the same starting material, but from an acid chloride, one equivalent of carbanion, so this is dimethyl cuprate, it is delivering methyl anion. One equivalent of carbanion will add. The electrons in the carbon-copper bond attack pi star CO in a nucleophile addition reaction, generating this tetrahedral intermediate. This tetrahedral intermediate can collapse, lone pair push, expel chloride in a nucleophile elimination step, generating the final ketone product. It is, same as here. And because this ketone product is less reactive than the acid chloride, it doesn't react any further with the cuprate and can be isolated. All right, great. Now we have learned how to add one equivalent of carbanion to a carboxylic acid derivative. It's just that that derivative is the acid chloride, it's not the ester. And just a brief reminder, if it had been treated with, instead of methyl cuprate, if it had been treated with methyl Grignard, the tertiary alcohol would be observed. So really this cuprate is special. It's less reactive than the Grignard. It doesn't react with ketones, so the ketone product can be isolated rather than the tertiary alcohol. Wonderful, so we have our elegant solution here. It's just don't use an ester. To add one equivalent of carbanion, we start with the acid chloride instead of the ester, and we use the less reactive cuprate. That was fun. Be sure to add this reaction to your chart. And choice of the cuprate, of course, depends on what R group is to be added to the acid chloride. I want to have that. We only have one more reaction to learn, and it's a big one. And we will get to it in just a moment. But before we move on, you should be sure that you understand how to fill in the second and fourth columns of the carbonyl grid. The most straightforward one is going to be acid chloride to ketone, because that one just directly involve the dialkyl cuprate we discussed. And maybe we should take a look at our copy of the grid that has the clues or the strategies on it. Here it is, yeah. So we can summarize the reduction quadrant. So what are the key reactions involved in the synthetic transformations in this section of the grid? And after you've thought about that, be sure that you can explain what each of these rules mean. Once you feel good, let's move on. Returning here to the carbonyl grid, let's think about what there's left to learn. Acyl transfer quadrant, we've got that. We just discussed this lower left-hand reduction quadrant, and there were certainly some keys, some new reactions that were really important that we learned. And I would say that really the most important reactions that we learned were the dival reduction of the esters to generate aldehydes, and then conversion of an acid chloride to a ketone directly with the cuprate. And that's going to be pretty useful for both the ketone column and the secondary alcohol column, because ketones, as we said, can be reduced to secondary alcohols. So if you can make the ketone from the acid chloride, you can also make the secondary alcohol from the acid chloride. because ketones can simply be reduced to generate secondary alcohols. You already know that transformation. All right, what is left to be done? Well, we have here several oxidation reactions, and most of them you actually already know how to do. So you could ask yourself, which of these do I know how to do? If you want, please pause and do that. But I'll tell you, these are the ones that you already know how to do. All these transformations of primary alcohols to all the different acid derivatives, you've got it. Aldehydes, you can convert those to ketones, you can convert those to all the acid derivatives, you're good. Now, where it becomes difficult is where we say take a secondary alcohol and maybe convert it into, well, anything that's not checked yet, but let's think about how we would convert it to a carboxylic acid. We have to break one of these bonds to one of the alkyl groups. Essentially, we have to lose a carbanion. How in the world are we going to do that? That's the case for all of these transformations. And in fact, thinking about the ketone being converted to any of these acid derivatives, yikes, one of these R groups, call it R prime, it's gone. It's been replaced with X. Where did it go? How can we remove an R group? You've been saying, you being me, over and over again, carbanions are not leaving groups. What in the world is going on? Yes, perplexing. I agree. Well, this one reaction, the only one left on our reaction chart, the Baeyer-Villiger oxidation of aldehydes and ketones. I spell it correctly about 25% of the time, so who knows if it's spelled correctly there. This one reaction will open up all the remaining spaces of the grid. Can you believe it? It's going to solve all those question marks. Okay, let's get to it. Let's get to this oxidation quadrant, top right. With a friend or with yourself, go ahead and describe the bonds that are made and broken for all the transformations described by this quadrant of the grid. These CH bonds that need to be broken, they can be removed through oxidation reactions, and we've done that before. For example, primary alcohols can be oxidized to carboxylic acids, represented by this square on the grid, upon treatment with sodium dichromate and aqueous sulfuric acid. So we've done that before. What we haven't done before, the bigger issue here, is remove carbanions. How can R minus be removed? Well, let's find out. We will have strategies for the oxidation quadrant. Here they are. Take a look at them. I am not going to read them right now. And now let's take a look at the Baeyer-Villiger reaction. When treated with a peroxy acid, such as MCPBA, ketones can be converted to esters via insertion of an oxygen atom between the carbonyl carbon and an alpha carbon. We will propose a mechanism for the example of this reaction that is shown on this page, and then we will consider, when have you encountered peracids in the past? Let's consider this question first. Who remembers when they've seen an MCPBA previously? Yes, and the conversion of alkenes to epoxides. Well, MCPBA reacts with a polar pi bond a bit differently. As you might expect, nucleophile addition occurs. You might not expect which oxygen it attacks or how it attacks, but nucleophile addition does occur to the carbonyl carbon of the ketone. That generates an intermediate that looks like this. The tetrahedral intermediate here undergoes an intramolecular proton transfer reaction to generate another tetrahedral intermediate that looks like this, with a good leaving group resulting from that intramolecular proton transfer. Now, collapse of the tetrahedral intermediate can occur, lone pair push. However, instead of this bond breaking, this is pretty cool, it's about to happen. Instead of this bond breaking, which usually is what happens, right? Lone pair push, X leaves. So instead of that happening, this bond between the carbonyl carbon and the alpha carbon, this bond, those electrons migrate over, break this weak OO bond, and that generates this ester product and a carboxylic acid derived from the peracid, which is a stable molecule and a good leaving group. Okay, if you're saying, what? Yeah, listen to that again. But this is a really cool reaction. And I will point out very quickly, ketones, which have two R groups, neither of which are leaving groups, like there are no leaving groups, we just converted it into an ester. And what does an ester have? So ketone to ester. Yeah, ester has a leaving group. Awesome. Now we figured out how we're going to do this, how we're going to remove these carbanions. We're going to turn them into alkoxy groups with the Baeyer-Villiger. Okay, cool, but let's get back to the Baeyer-Villiger because we're probably a bit confused. Let's continue to look at this reaction. So we just saw the Baeyer-Villiger for a symmetrical ketone, believe it or not. That's what we did. That was symmetrical. We could have looked at it for acetone. If it was treated with MCPBA, only one of the alkyl groups would migrate. And it doesn't really matter which one migrates, right? Because they're the same. For unsymmetrical ketones, just like for the symmetrical one, only one of the alkyl groups will migrate. But for the symmetrical one, there was really no decision to make because the two R groups were exactly the same, right? Methyl and methyl. So the two R groups are the same. They're not going to be the same for an asymmetrical ketone. Like that's kind of why it's not symmetrical, because the R groups are not the same. So you can imagine that upon oxidation, either R prime could migrate or R could migrate. And these are two different esters. It's not ideal to get two different products or multiple products from a chemical reaction. All right, well, the good news is that different alkyl groups migrate at different rates. So there actually can be some selectivity in these Baeyer-Villiger reactions. So looking at these groups, I will list them for you from those that undergo the fastest migration to those that undergo the slowest migration. So hydrogen migrates more quickly than tertiary, which is more quick than secondary, which migrates about the same rate as phenyl, which is faster than primary and is faster than methyl. Methyl is the slowest. For example, if there was an aldehyde, such as this one, was treated with MCPBA, you would look at the two groups bonded to the carbonyl carbon. So let's just label all of our carbonyl carbons on this entire slide. And there are two atoms bonded to that carbonyl. There's hydrogen, and then there's the alpha carbon. All right, well, hydrogen migrates faster than a tertiary carbon. So what would the product be? The product would be the carboxylic acid. Oh, that's cool. That's a direct, nice way without chromium to convert aldehydes into carboxylic acids. I'll look at another example. We'll just change it up a bit. We'll just turn that aldehyde into a ketone. We'll just swap the hydrogen for a methyl group. If treated with Baeyer-Villiger conditions, take a look at the two alpha carbons. One of them is methyl, one of them is tertiary. Tertiary migrates faster than methyl, therefore the following product will be observed. This ester, where the tertiary carbon migrated. Oh, this is fun. We just have to apply the rule here. All right, we have several practice problems, but this video is pretty long, so I'm going to wrap it up and say time to celebrate. The Baeyer-Villiger reaction just opened up the rest of the grid. So for these two rows where we were so concerned because we didn't know how to break these carbon-carbon bonds, now we know. We'll do one for example. So let's do this box for example. So we have a ketone, want to convert it to a carboxylic acid. First, Baeyer-Villiger oxidation generates the ester. assuming hopefully R prime migrates faster than R. It really depends on what the two alkyl groups are. And then we know that esters can be hydrolyzed to carboxylic acids. We learned that in the acyl transfer. So we'll just use catalytic acid. All right, and that's an example for you. And you'll have to use Baeyer-Villiger for secondary alcohols as well. Are you going to give that a shot? You are ready to fill out your entire carbonyl grid. Don't forget about the off-grid reactions. Today we learned about making tertiary alcohols via Grignard additions to acid derivatives. And we learned about reactions to make primary alcohols and reactions of anhydrides. You have learned how to predict the products of redox reactions to carboxylic acid derivatives. You can provide complete curved error mechanisms for those reactions. Evaluate the relative reactivities of carboxylic acid derivatives in common reducing reagents. This was so key today to thinking about how to add elegantly one equivalent of hydride or carbanion to various acid derivatives. And then finally, you'll need to practice proposing synthetic pathways involving oxidation and reduction reactions of carbonyl compounds as key steps. And your carbonyl grid will allow you to do that, right? That's why we're making this grid. It is a synthetic tool. And these hints will help you in proposing those synthetic routes. Like for this box, oh, I need to go through the ester. Okay. Summarize what you've learned today. Ask me any questions that you have. And then as always, it is time to practice.